onto polynomials. So this is something I talked about a little bit before. Polynomials are when we have something to the power of x, x to the power of something. So you can see, this is a quadratic. It's ax squared plus bx plus c. This is a cubic, y is equal to ax cubed plus bx squared plus cx plus d. And we have quadratics, y is equal to ax to the power 4 plus bx cubed plus cx squared plus dx plus e. Okay. The only information that, that this expanded form tells us is the y-intercept. And that's because if I do, again, I'm just going to get my pen out, the y-intercept happens at x is equal to 0. If I do that, this will tell me that the y-intercept is equal to c. Here the y-intercept is equal to d, and here the y-intercept is equal to e. That's because when x is equal to 0, all of these terms here get cancelled out, because they're all 0 terms, right? Okay. Hopefully that's something that makes sense. All right, I'm going to move on from this form. Okay, factorized form. So factorized form is a lot easier to deal with. I think visually it also looks nicer just because everything is bunched together. So this will tell us what the x-intercept looks like. Though keep in mind that not all polynomials can be expressed in this form, and you'll definitely come across polynomials that you can't factorize, and with those it's a little bit harder. Generally, non-factorizable polynomials don't have x-intercepts, so that's a pretty good rule to keep in mind. And if a polynomial, yeah, so this is basically what I said. And also x-intercepts happen at y is equal to 0. So let's say the quadratic. I'm going to set y is equal to 0, and that's going to be equal to a times x plus b times x plus c. We can divide both sides by a, and so we'll get 0 is equal to x plus b times x plus c. Okay, have a think about how we would go from this into finding the x-intercepts. See if you can come up with any solution to this one. Again, I'll give you guys about 30 seconds to think of that. Okay, so hopefully you guys maybe could have come up with a method. If not, that's perfectly fine. This is a weird sort of rule. It's called null factor rule. And that basically says if we have two numbers, let's say we have a and b, if we have two numbers that multiply together to get 0, either a or b is equal to 0. So a equals 0, or b is equal to 0. Which makes sense, right? If we have 4 times 0, well, one of those numbers is definitely 0. Any two numbers times 0, one of them always has to be 0. It doesn't even have to be two numbers. Any 3 numbers, any 4 numbers times 0, one of those 4 numbers has to be equal to 0. So that's what we're using here. So what we can say is either x plus b is equal to 0, or x plus c is equal to 0. And then from here, we can resolve for b and c. So our x-intercepts in the quadratic case would be x is equal to minus b, and x is equal to minus c. All right, so hopefully that makes sense for everyone. Okay, so let's talk a little bit about what the different forms of factorization are. So here you will see that everything is to the power 1, right? But sometimes with quadratics, what we can have is a repeated factor. So in some cases we can have, or even with cubics, right? Sometimes we can have x plus a squared times x plus b, right? What does that mean? we have two of the same factors. Like, how do we deal with that? Um, whenever something is raised to some power, right? The type of intercept it is will change. If it's to like a linear power to the power 1, it's just going to cross the x-axis normally. If it's squared, it's going to become a turning point. It's going to like parabolically touch the line and move on like so. And if it's to the power 3, we'll get this weird, cool shape like this. And this is called a point of inflection. I'm going to write POI. Sometimes it's called stationary point of inflection. You'll probably come across that more in E11, but it's called stationary point of inflection, usually. That's when we have something to the power 3. You'll only really see that in cubics and quadratics. Okay. And one of the other forms, and probably the last form I think we're covering today, let me just check. Yeah, is stationary point form. So stationary point form of a polynomial is going to be sum plus c value and everything else in this squared or cubed or quadratic bracket. Again, not all polynomials can be expressed in this form. If they can't, they probably don't have a stationary point. Quadratics are always expressed, like can always be expressed. So for quadratics, this is going to be a turning point. For cubics, this is going to be, those point of inflections I was talking about earlier, this stationary point of inflection. And for quadratic, that's again going to be a turning point. Maybe some of you guys haven't seen a quadratic. I'll try pull up Desmos and see if I can get you guys a nice sort of image. If you haven't seen a quadratic, I think I'll do that now. I'm just going to quickly switch on to Desmos. Graphing calculator. All right, so x to the power 4. Is there an easy one? Oh, yeah, x to the power 4 looks a bit like this, right? X to the power 2 looks like this, and all the differences you can see is that x to the power 4 is just steeper, right, at the start. But x to the power 4 can have a lot more wonky shapes. You know, if I add an x, it changes in shape straight away. If I make that x squared, it goes back to being normal. If I make, another x, again, weird. If I make it a 3 and then add x, it becomes even weirder, right? So we can have all sorts of shapes with x to the power 4, whereas with x squared, it's always going to be this same sort of shape. All I'm doing here is shifting that turning point, right? Okay, hopefully that makes sense. I'll also show you guys cubics. So cubics, you can see already it has that weird shape, but sometimes it won't always have that. So if I do plus x, that shape changes. If I do plus x squared, now I have this sort of bumpy shape. I'll see if I can make that larger. So we'll zoom out. Oh, 10 is probably too big. Try 5. You can see, from here, we can tell that this factor here is going to be an x squared term, right? That's sort of like, it's going to be like this term that I was talking about here. I'll just switch back to the PowerPoint. It's going to be like this. And the reason I can tell is because, it goes down and then goes up. All right. Hopefully that makes sense with everyone. And yes. Oh, cool. I think we're back. It's a little bit slow, but I think it dropped out for a little bit. All right. I'm not sure where it dropped out, but yeah. Okay, I'm gonna turn off my camera, just because it did this a little bit yesterday, and I don't want it to keep dropping out, in and out. But yeah. Okay, so I'm not sure exactly where we left off, but hopefully it wasn't too long ago where it dropped out. So what I was talking about is the different types of stationary points and where they happen. This one is a cubic stationary point, stationary point of inflection. This is the quadratic in its stationary point form, and this one here is the quadratic in its stationary point form. All right, let's switch back to this. All right. Again, I'll give you guys some time to have a go at completing the square, and then we'll try to get into it. Just to recap, this is going to give us a turning point, a stationary point of inflection, and a turning point, and that happens at negative b, comma c, right? So just keep in mind, if we're doing something like x minus 4 squared plus 5, that's going to become 4 comma 5. All right, have a go at completing the square, and then we'll walk through it. All right, in the meantime, I think I'll check the questions. Yeah, every SAC to get a 50 study score. Honestly, this isn't a question I can really answer. It depends. Sometimes yes, sometimes no. I'm not too sure. Again, your exam is worth 60% of your study score. I'm not sure what sort of percentage you need to get on your SACs. Like, it changes from school to school. Sometimes, like, schools set really hard SACs, and in which case you might not need to, or you might. I can't give a definite answer on that. I don't know how VCA works. Unfortunately, I would love to know, but yeah, I don't really know myself. I'm really sorry about that one. But yeah. Um, but if you are aiming for a 50, you want to be getting the highest scores that you possibly can. Um, it's really hard to get a 50. Only 30-ish people get a 50 every year. So yeah, I'm not sure, but if you are aiming for a 50, you do need to give this subject like your all. You need to like definitely like just try your hardest, put in like 100% of your body into this one. But yeah, sorry about that. Um, I think I'll get to this a little bit later. And how would you go about resolving or working on reducing silly mistakes? Well, one of the things I pointed out earlier is doing everything step by step, not skipping algebraic manipulation. Also, throughout the lecture, every time we do a question, I'll point out wherever we can work on reducing silly mistakes, because silly mistakes was a big part of like it was a big headache for me in year 12, especially. Not something I noticed too much in year 11, but in year 12 I definitely noticed it. I'm not sure because if the pressure got higher and I started getting stressed a bit more, but yeah, no, I made a lot of silly mistakes in year 12. So we'll definitely talk about that throughout the lecture, because I think it's a very important thing to talk about, and maybe people don't talk about it enough. Okay, all right. We'll get with the lecture. We'll get on with the lecture, and I'll get to these later. But yeah, I think I'll definitely try to answer all of these questions. Okay. All right. So to convert a quadratic into expanded form, we can do the thing completing the square. So hopefully you guys, brainstorm ways we can actually complete the square, or what even completing the square means. Okay. So all we do is we halve this term b. So we're going to halve it, and then we're going to square this new term. And then we add this term to make this perfect square. What I'm talking about when I say a perfect square is x plus a squared. That's what I'm trying to make here. If you guys remember, this gets expanded, so x plus a squared gets expanded into x squared plus 2a times b plus b squared. So that's what I'm trying to do here. I'm trying to make this form here. Okay, so how do I go about making this form? So the very first step is to make sure that a isn't really there, and we sort of have to like pull that out, factorize it, maybe get rid of it. Depending what number here. Wait, I just did something wrong. Sorry. You guys probably saw my mistake as well. The b shouldn't have been there. should have just been 2ax plus b squared, or plus a squared. I was looking at that and I was like, that looks really wrong. Yeah. Anyways, that's another good thing to pick up about silly mistakes. Oh, I just did it again. All right, that's really annoying. That's another thing to pick out about silly mistakes. Every time you write a line of working out, read it again and read it again and read it again to see if it makes sense to you. If it doesn't make sense to you, something has probably gone wrong, and you should probably fix something about that there. Okay, so let's say, we have some term x squared plus bx, right? Let's ignore the c for a bit. And I want to somehow, like factorize this perfectly into a square. How do I even do that, right? I somehow want to try get x plus b squared. That's what I want here, right? Um, how would I? Well, I don't want x plus b squared. I'd rather actually want x plus b over 2 squared. And the reason I'm doing b over 2 is because see this 2a is here. So hypothetically, if this is expanded, I want b in the middle, right? So if b over 2 is times by 2, I'm going to get b. If that's a little bit confusing, just hang on. It might make a little bit more sense later on. Okay, so if I expand this, I'm going to get x squared plus 2 times b over 2, which is going to give me b times x, which is bx, and I'm going to get b over 2 squared. What's b over 2 squared? Well, b to the power 4 divided, oh, sorry, not b to the power 4, b to the power 2 divided by 4. So b squared over 4, yeah. All right, so that is what a perfect square is there, right? So I'm going to try and make a perfect square from this. So how do I do that? So the first thing is, well, I know, I can take this, so I can take b, I can divide it by 2, and I can square it, right? And we've already done this, but I'll do it again. And that's going to give me b squared divided by 4, right? And now I can add b squared, but just to make sure I don't change the equation entirely, I'm also going to subtract b squared, right? Otherwise, because b squared over 4 minus b squared over 4 is going to be 0, so this equation hasn't changed at all. But if I just added b squared without, subtracting it, well, I'm now dealing with a different equation, and then all of this doesn't actually matter at all. So yeah, subtract it so that the overall expression is the same. And so now this part here is this perfect square here, which is pretty nifty. So now we can just factorize that here. I think it'll do for me, yeah. So now we can just factorize this into this. And then the very last thing you need to do is solve for this term here. So hopefully that makes sense with everyone. I'll get you guys to do a question on this as well. Have a go at doing this. Use the same sort of method that we used. So define your terms. Find what b in this case is. Half b divided by 2. Or yeah, it's the same thing. Divide b by 2 and then square the product and then add it and then subtract it. In this one, I'll give a bit of a hint. Keep in mind the negative term. That's something to be wary of here. So I'll give you guys 2 minutes to have a go at this one. Maybe 2 minutes is a bit long. I'll give you guys a minute to have a go at this. Okay, I think it's about time. Maybe I'll give you guys a couple more seconds. Sorry, I think my allergies have kicked in today, which is not great, but yeah, going through. Okay, how would we go about doing this? Oh, just skipped over that one. All right. I wonder if I can type. All right, typing apparently is not allowed. All right, so first thing, I want to determine what my b term is. So what I'm going to do is I'm going to split it up so that it looks a lot more like this. So that it looks like x squared plus bx plus c. So what I'm going to do is x squared plus minus 6x plus minus 1. Okay, the next thing to do is to get minus 6, divide it by 2, and then square it. Again, I'm going to do everything in single steps just because it's easy for you guys to follow, and also it prevents me from making silly mistakes. So this is what I'd actually do on my exam. So negative 6 divided by 2 is going to give me negative 3, and then I'll square this, and from here I'll get 9. Cool. Let's see if that is correct. Pretty sure it is. Looks all right to me. Okay, so now I'm going to add it and I'm going to subtract the term. So I'm going to get x squared minus 6x, or I might keep it in the same form, just so we don't get confused, minus 6x. Sorry about that. That's just pretend this doesn't exist. Pretend that's part of the brackets. Plus 9 minus 9 minus 1. Okay, cool. So now what we have here, that is our perfect square. So what we can do is just factorize this, right? So I'm going to get x, so it's going to be in the same form as this, right? So it's going to be x plus negative 6 by 2 squared minus 10, which is going to give me x is equal to minus 3 squared minus 10. All right, who thinks we're done? Well, obviously I can't see, but if you think you're done, you'd be wrong. Just because it says plus here, they want it in the form of this. Whenever they ask for a specific form, if it doesn't look exactly like this, they won't give you the marks for it. So what we need to do is we need to somehow change this to a plus. How do we do that? Well, we can. How do we do that? Have a think. We'll let you guys try to figure this one out on your own. Okay, so with the plus b bit, it's a bit of a cheesy way to get around it, but you can just throw in a plus here and put brackets around this. And then maybe you can take a negative out to get this. Well, actually, or you can just do the same thing. You can just like cheese it, sort of show a plus here, put a negative 10 in the brackets. So then c is equal to negative 10, but that plus is still there. It's a bit weird, but this is the sort of things that make VCAR and their, assessors and your teachers a bit happier. Just so, they know that you're paying attention to the detail with that. All right, have a go at this one here. Might be a little bit more tricky. Keep in mind, for us to be able to complete the square, we can't have anything in front of the x. It always needs to be 1. And here it says 3. So think about what you can do about that and how you can get rid of that 3. I'll give you guys about a minute to have a go at this as well. Okay, hopefully you guys are able to have a good go at that. I don't know if it has been a minute yet. Maybe I'll give it a couple more seconds, just in case it wasn't a minute. Let me just see if the stream is still as well. Okay, nice. Um, I'm gonna see if I can get rid of the camera just to make it a little bit better. Actually, not be bothered. All right, let's get into this. All right, how do we go? How do we get around fixing this issue with 3? Right? How do we work with this? Well, simple answer: factorize. So, congrats to everyone who found that. All we have to do here is just factorize. So I'm going to pull the 3 out, and we're going to be left with x squared minus 2x minus 1 over 3. Ooh. I guess we'll just have to deal with that. All right, here's a shortcut. I know my final term has to always be in the form x plus b over 2 squared, right? Wait, did I make a mistake earlier? I'm just trying to think. No, actually, it's all good. No, this is fine. Sorry. Okay, so I now know that I can sort of chuck it into that form, but I don't want to do that because it's a really easy way to make silly mistakes. So we're going to still do it step by step. So b, in this case, is going to be equal to negative 2, right? So what I'm going to do is I'm going to half negative 2, and then I'm going to square it. So that's going to give me negative 1 squared, right? And negative 1 squared is just nicely 1. It's pretty neat. Now I can subtract it and add it in, but I can only do that inside the brackets. So x squared minus 2x plus 1 minus 1 over 3 minus 1. Okay, hopefully that's all good so far. But what goes in the brackets is the unsquared version. What goes in the brackets is negative 1, or negative 2 divided by 2, right? We have a look here. It's going to be b over 2 that goes in the brackets. So then we're going to get x minus, but we want it in the form x plus b, right? So x plus minus 1 in brackets. Again, sorry for the really janky brackets, x squared. And then we're going to do minus 1 over 3 minus 1. Again, I'm going to split this up into multiple steps just to prevent making errors. Minus 1 is going to be 3 over 3, right? And this is going to give me x plus minus 1 squared plus, this is going to be minus 4 over 3, right? Because minus 1 minus 3 is going to be minus 4 over 3 plus minus 4 over 3, and we're done. That is now in its completed square form, which is pretty nice. Good stuff to everyone who got that one. That's a little bit more harder than the last one. Okay, so how are other ways we can factorize things, right? This is one way to sort of factorize weird things, right? Sometimes it's harder to factorize things like this, but what are other ways we can factorize stuff? Or solve, sorry, what are other ways we can factorize things or solve quadratic equations? And it's given by the quadratic formula. One question I'd encourage you guys to ask is what or how do we get the quadratic formula? And the answer to that is we get this general term, ax squared plus bx plus c, and then we complete the square on this. So we get this term, and then what we do from here is complete the square. So c, t, s. Have a go with this in your own spare time. It is an interesting exercise, really heavy on algebraic manipulation. But yeah, definitely recommend trying that out. Here's the derivation, so you guys can have a go and then double check it and see how you did here. You can see in this very first step, what they're doing is dividing both sides by a to get rid of that a though, right? You can see that though. Okay, so I'll get you guys to have a go at that, later. But definitely come back, check it out, see if your answer was correct. So the quadratic formula comes from completing the square, like I said. And then after we complete the square, right, we don't just stop here. What we do is we then rearrange and solve for x, right? We subtract this term to the other side, and then we take the square root. Remember, when we take square roots in general, we do plus or minuses. You guys will remember the last time we did a square root was for the distance formula. And you can remember that I didn't do this plus or minus. Does anyone have a guess as to why? Well, take the guess. Obviously, I can't hear you. But the reason that we can't do a plus or minus is because distance is a positive measure. Distance is a magnitude. So it's just like the length of a value, really. Distance is just the length, right? So it doesn't matter. Well, like distance can't be negative. So I'm not going to take the negative side of it. It doesn't make sense. Sorry, I'm just going to quickly grab a tissue. But yeah, it doesn't make sense. So that's why I ignored ignored the negative solution when I took the square root earlier, because it just doesn't work out well. All right, try using the quadratic formula to have a go at this question here. I'll give you guys about a minute or so to have a go at that one. In the meantime, I'll check if the stream is still up. Hey, nice. Also, if the stream does go down at any point, feel free to shoot me an email to make sure I've seen that the stream has gone down, because sometimes I don't see it from my end. I have to go and manually check. Okay, hopefully that was enough time to apply the quadratic formula, play around with it for a bit, and see how it works. I think another thing to note is the quadratic formula isn't on your formula sheet from memory. Could be, but I'm pretty sure it isn't. Ideally, you want to remember every single formula, and obviously this is one of those formulas you will have to remember. But I think you'll use it like a lot, right? It's a formula that you'll end up using a lot. I actually prefer using this formula than factorizing in most cases, just because it's a bit easier for me. All right, so let's try use our quadratic formula. So x is going to be equal to minus b, which is minus times minus 4. So minus 4 plus or minus b squared, which is going to be this again. So minus 4 squared minus 4 times 2 times minus 3. And all of this here is under a square root, divided by 2 times 2. So if you got here, good stuff. You plugged everything into the formula correctly. Everything it is from now is just a bit of algebraic manipulation, well, not algebraic, just a bit of, crunching numbers, really. Okay, and making sure you don't make any silly mistakes. So the very first step is to multiply the negative in, so we'll get 4. The reason I've done everything like this is so it prevents me from forgetting about negatives and so on. We'll do plus or minus. What's negative 4 squared? It's going to give me 16, right? And it's going to be minus 8 times minus 3, right? So what's 2? 2 minuses are going to be multiplied, so it's going to be a positive. And 8 times 3 is going to be 24. in an exam, I'd be talking to myself in my head as I do that, just reminding myself that, that's how maths works. And 2 times 2 is going to give me 4. All right, neat. What is 16 plus 24? The way I like to add numbers like this, because it's pretty prone to making mistakes, is I do 10 plus 6 plus 20 plus 4. And this prevents me from making addition mistakes. So 10 plus 20 is going to give me 30. 4 plus 6 is going to give me 10. So it'll be 30 plus 10, which is going to be equal to 40. Nice. So it's going to be 4 plus or minus square root 40. Well, this square root is simplifiable, right? Because 40 is going to be equal to 4 times 10. So if you guys remember simplifying surds, hopefully that's something you guys remember from your earlier years. 4 times 10 can be broken down into something a little bit simpler. So 4 plus or minus 4 times 10. The square root of this can be pretty easily broken down. I'll get to that in a minute. Sorry, it's very slow writing the mouse pad. That's going to give me, when I take the square root of 4, that'll give me 2. And the square root of 10 is just going to stay as the square root of 10. So it's going to be 2 square root 10 by 4. And I can break this down one step further into, I can split it into 2 fractions. So I'll have 1, because 4 over 4 is going to be 1, plus or minus 2 divided by 4 is 1/2. So that's going to be 10 square root of 10 divided by 2. And that is what x is going to equal. So congrats to everyone who got that. If you left it, if you like just divided by 2 from here, so it'll be 2 plus or minus root 10 over 2, that's perfectly fine as well. You can either split it into 2 fractions or you can leave it in the 1 fraction. Doesn't really matter. I just prefer it like this, so I do it like that. It's personal preference, really. Oh, it's here as well. Let's see if we got it right. Nice. They just didn't simplify it here in this solution. But yeah, the best way to avoid making those tiny errors on a non-calculus test is making sure every single step is written out and every single point of working out is written out. The one part I skipped was I went, I went from -4 times 2 times -3 to 24. I shouldn't have done that. I should have gone -4 times 2, which is -8, written that down, and then multiplied that by -3. I just did it because I got a little bit lazy with writing with the mouse pad. Okay, I'll get you guys to have a go at this one as well. Let's quickly check how long until the break. Oh, there's a few. All right, sorry. Just checking if the stream. I'll give you guys a couple more seconds and then we'll go through this. Okay, let's go through this now. All right, so we want to be using the quadratic formula and trying to find a way to figure this out using our quadratic formula. So it's going to be the same method that we talked about, here. So the very first step is to plug everything into our quadratic formula, right? So I'm going to do, that's my b term. Really, it should be minus 4 times -1, right, at the front. And that's going to collapse to 4, right, which is nice. This is going to be, again, ooh, has there been a mistake that has been made here? Is this the same question? Yeah, it is the same question. Oh my God, I didn't even realize. That's my bad. They got to the same answer. Oh, that is on me. I thought that was a different question. Oops. All right, sorry about that. Okay, so this is something that we didn't do though. This is graphing that formula. So have a go at graphing it. I'm really sorry about the last slide. I did not realize that was the same question. But yeah, have a go at graphing it and we'll talk about what it would look like. Alrighty, let's get onto this one here. All right, so how do we graph things? How do we graph this, right? So generally, when we graph things, a few general steps that I always like to tell my students is that one, always draw out like well after you've drawn out your x and y axes, label your x and y axes, because unfortunately, like Vika will actually deduct marks for not labeling your x and y axes. The next step after making your axes, labeling them, is to find out your x-intercepts, your y-intercepts, your turning points or stationary points. If there are any asymptotes, find asymptotes. If you don't know what an asymptote is, you'll get onto it later on in the year, so don't stress about that. And that's sort of it. After you're done with that, you can sort of move on. After you've sketched your graph, you need to make sure that you've labeled your x-intercept, your y-intercept, and at the end of the graph, you need to make sure that there's arrows labeled at the end to show that it is continuous, if it is continuous. All right, so hopefully you guys got something like this. We have one x-intercept at our negative solution and one at our positive solution. In this case, the turning point hasn't been labeled, but I do recommend that's something that you guys should do. So let's try to work out the turning point in this case. With quadratics, it's really nice and easy to work out our turning point. All we do is we take this and we add it to this. So pretty neat there. So we're going to do minus square root 10, and then we divide the end result by 2. So we find the average really between the 2 points, plus 10 square root 10 plus 2 divided by 2, and all of this is going to be divided by 2 again. So that's going to give, all of that's going to cancel out. So this is gone, and I'm going to be left with plus 4 over 2 divided by 2, which is going to give me, this is going to crash into 4 over 2. I mean, sorry, 4 over 2 is going to simplify into 2 over 2. It's going to simplify into 2, and that's going to be divided by 2. Sorry, don't know what I'm saying. And here we'll get 1 as one of our, that's our x coordinate for our turning point. Next, we need to go and figure out our y coordinates for our turning point. So the way I'll do that is I'm going to do f of 1. So I'm substituting 1 into here. And that's going to give me 2 times 1 squared minus 4 times 1 minus 3. And that's going to give me 2 minus 4 minus 3. Okay. And this is going to be equal to 2 minus 7, which is just going to be minus 5. And this matches up with how the graph is, right? It matches up with these numbers here, and it matches up with that. So that's going to be 1 comma negative 5. And since this graph is continuous, what I like to do at the end is just throw in these little arrows that show it is continuous. If it's not continuous, keep in mind that a closed circle like this, a colored in circle, that represents inclusive, and an open circle like this represents non-inclusive. So hopefully that makes sense. Alrighty, so let's just look at the quadratic formula and talk about this thing called the discriminant. Maybe it's something you guys have heard about before. It's a pretty useful property that a lot of that we can use a lot in problem solving. And yeah, so let's get into it. So we can see that this term here, the b squared minus 4ac term, can't be negative just because we can't have negative numbers in square roots. If you guys are doing specialists, you will cover complex numbers at some point. And complex numbers, interestingly, are numbers that have a negative square root. So, it's like 5 plus the square root of negative 5. It's things like that. That's a complex number, but that's not going to be covered in methods. And so in methods, we only talk about real numbers, and real numbers are when when you like take the square root of a positive number. That's a real number, really. So yeah, so b squared minus 4ac needs to be greater than 0. So because of the plus or minus, we're given two options if the b squared minus 4ac term isn't 0, right? And so now this is known as a discriminant. And it generally has a symbol of this triangle thing here. So when our discriminant is equal to 0, there will be only one solution because that plus or minus isn't there. So like imagine if this part of the graph isn't there, right? It's just going to be plus or minus 0, right? So then our only x solution is minus b divided by 2a. But pretending that this is there, now we have plus or minus, so we can plus this or we can subtract it, so we'll get two solutions. If the discriminant is less than 0, well, we can't compute this in the real numbers, right? There is no real solution. So that for that we say, so no real solution. So no real solution. And so that means there are no x-intercepts. No x-intercepts. Pretty nifty. But yeah, that's that. So hopefully that makes sense. We can use it a lot in a variety of different types of problem solving, especially in year 12. So this is something you should definitely hang on to. Same with the quadratic formula and same with everything we've talked about so far, you need to hang on to when you get into year 12 as well. All right, so what does this look like graphically, right? So if we have no solutions, it's just not going to touch the x-axis. If it has one solution, it'll touch the x-axis once. And that generally means that there's a turning point though. And if it has two solutions, well, then it'll look like a normal quadratic with the two solutions there. This is x squared. This term here, this is just y is equal to x squared, right? If we try work out the discriminant for this, our discriminant is going to be b squared minus 4ac. This doesn't have a b squared term or a 4ac term, so it's just going to be 0. And so that matches up with what we see. All right, have a go at this. This is a pretty cool application question, I think, or problem solving question. Oh, sorry. But yeah, have a go, and I'll give you guys a couple minutes to do that. In the meantime, I'll just check if the stream is still. Okay, hopefully that was enough time to have a go at doing this question, and hopefully you guys got the solution. All right, so find the values of m for which the graph of y is equal to f of x has exactly one x-intercept. Okay, so what sort of things are we looking for, right? One of the things we're definitely looking for here is a discriminant of the value of 0, right? So we want our discriminant to equal 0 here, right? Because that's what tells us when it has one solution, discriminant of 0. Okay, so let's create our discriminant equation here. So this is our b term, this is our c term, and our a term in this case is going to be 1. So we'll get m squared, so b squared, minus 4 times a, 4, sorry, times a, which is 1, times c, which is 4. Okay, cool. And we can equate this to 0. Well, for now, we'll just say this is our discriminant. And now our discriminant is going to be equal to m squared minus 16, right? And now we can equate this to 0. And we'll get m squared minus 16 is 0. And now solving for this gives us m squared is equal to 16. And from here, m is equal to plus or minus 4. Cool. One thing that like sort of hints that we'll need multiple solutions for m is that it says find the values, like plural s, values for m of m for which the graph y is equal to f of x has exactly one x-intercept. So m can equal 4 or m can equal -4. Also, I did skip a step here. Like, how did I go from here to here? All I did was I took a square root. So did m is equal to plus or minus the square root of 16?